Hi. So I'm a fourth-year PhD student at UC Riverside back in California. I done my PhD work on this thing called the matrix profile. The matrix profile is essentially a way for time series analysts to examine their data and gain more insights. So I think the best way to is just to get started. So I'm going to go over what the matrix profile is. I'm going to go over some of its applications, and then I'm going to spend about half of the talk specifically talking about how we scaled up its the ability to compute it, and how that's very important if you actually want to deploy it and use it in a real system. And then I'll go a little bit more into detail about some future work that I'm working on. And unfortunately, the title is a little misleading. I originally intended to talk about something slightly different. So I'm relegating some of what's here to near the end of the talk. So sorry if you were coming for real-time pattern mining, but it's not quite there yet. Okay. So what is the matrix profile? So let's start with an example. So let's start with just a synthetic time series. And when we refer to time series, we're basically just talking about a sequence of real values. So in this case, we have some noise, and then inside the noise, we've inserted these sine waves. And essentially, what the matrix profile is when you're concerned about small sequences or local sequences or shapes in the data, essentially you can use the matrix profile to uncover what's called motifs or anomalies in the data. So I'm going to kind of introduce the matrix profile here. I'm not going to talk about how to compute it initially. So imagine you have this time series and you're concerned about sequences of length 100 in it, right? So you're going to do a scan across the whole time series looking for matches or patterns of length 100 that reoccur in the data, okay? So here's the matrix profile in blue for this data set. So you can see that it records the location and distance to the nearest neighbor in the time series. So essentially, starting with essentially what happens is it points out so these low values here correspond to motifs in the data set. So as you're scanning along sequences of length 100 in this data set, you're scanning along, you're looking for its nearest neighbor. This is all noise, so we're not gonna find anything. But as you get farther along, you're gonna encounter this sine wave, and that sine wave appears here, and it appears here. So you're gonna get this increase in similarity or decrease in distance to this pattern as you get closer and closer to it until you get to the start of the pattern, in which case you hit the local minima, right? And we use z-normalized Euclidean distance. So in this case, we're not looking at the scale of the data. We're looking at pretty much only the shape of what the pattern actually looks like. And so this could be an advantage and a disadvantage. I'll go into that a little bit later. But you can adapt the matrix profile to different distance measures as well. So we also have, if you're computing the nearest neighbor, you can also compute the index, and you can keep track of it. So you can also basically track what you have an index here. So you have a match here, and you can also track where it occurs. So you basically have a pointer to the other place where it occurred. And technically, this pattern occurs 3 times, right? So there could also be, this guy's nearest neighbor could be here. In the end, you're gonna find all the patterns. They might not all, you might not get all the information because we're only looking at one nearest neighbor. But traditionally, it's actually enough information, especially when your time series gets large. which I'll go into later. So why is it called a matrix profile? Well, the matrix profile, it's called a matrix profile because it's a profile of a distance matrix. The distance, a naive way to compute this would be to construct this entire matrix of distances between subsequences. Of course, since this is the same time series, it's actually a symmetric matrix, and so the upper triangular portion is all you have to compute, and then there's some overlap of like trivial matches where you don't want to, you of course don't want to match. So in this section, you could track the entire matrix, and then but that would be just too expensive, right? If you have 1 million data points, that's like 4 trillion, 4 terabytes just to store the distance matrix for 1 million data points. So you don't want to do that. So essentially, I want to say that we can compute this very efficiently in terms of space, and we can also perform many optimizations in order to actually make this computation a reality. So let me go over how to read a matrix profile. So I talked about this a little bit earlier, but essentially you have high regions in the matrix profile. I haven't plotted the original data here, but you have high regions in the matrix profile which correspond to essentially anomalies. These are subsequences whose nearest neighbor was nowhere nearby anything else in the data. And so this implies that this is an anomaly. Now, the low values correspond to motifs or repeated patterns. They usually, they will at least come in a pair, but sometimes you'll have more than 2 occurrences. In fact, that's often the case, because if you're monitoring the behavior of a system, that system is going to have if that system has some periodic nature, then you're going to end up recording similar patterns multiple times. And so this is so I think, let's go. So applications of the matrix profile. So just one example, we have some taxi data from the fall of 2014. We actually can compute the matrix profile for this data, and it's about, we're going to use a subsequence length of 2 days. So what we get from that is we actually get 3 discords, or 3 anomalies, one located around Thanksgiving, which is when taxi traffic drops because people are at home or not around. And then you have another one here in the middle, which is actually corresponds to, it's actually an apparent doubling of taxi load, because what's happening is this is daylight savings time, and so when when daylight savings time occurs, taxi traffic is bucketed into the same hour for two separate hours, and so you have this doubling here. And then this one is a smaller thing similar to Thanksgiving, but this is actually Columbus Day, and because it's normally Columbus Day is not celebrated in the United States, but in New York there's a large Italian American community, and so we actually you can actually see some things happening here. And this is just another example. So we're just looking at a periodicity of, there might be a periodicity of larger than a single day here. So you can actually have like weekly periodicities, right? Because on the weekends, the traffic might be different than during the weekdays. So you can actually have these kind of multiple different lengths of subsequence that could also give you different insights. Here's an ECG. So in this ECG, you have a premature ventricular contraction, which is actually it's relatively common, but it can't. If they happen a lot, they can actually indicate life-threatening conditions. And same thing with ectopic beat. but essentially, this data looks very similar, right? Except for we have these discords here, which occur when these abnormal occurrences happen, right? So another example, seismology is a big example here because when you have an earthquake that occurs in the same place actually generates the same ground waves to the same place you're measuring. So in the case of an earthquake that happens, say, in one particular location and you're measuring it from the same place, you can actually record a repeating event in the data regardless of the magnitude of the signal. So you could have a magnitude 7 earthquake and a magnitude 1 earthquake, and they could actually be similar in terms of their seismic signal. And so in this example, we actually have a magnitude 1.2 and a magnitude 1 that occur. These actually occur like about an hour apart, I believe. So, and they're in the same position in latitude and longitude. So we've actually used this property to mine. I'll talk about it later. We mined about 2 years of data at 20 hertz exactly. So we took data from a place in California and actually ran this experiment and did an exact search of 1 billion data points. And I'll show you how I did that with optimizations later. So you not only can do a self-similarity search, you can also do a similarity search across time series. So if you have, for example, this is actually a song, and this is another song, and we're looking for a pattern about this length, which occurs somewhere in the data, right? And what this actually is this is Queen's Under Pressure, and this is Vanilla Ice's Ice Ice Baby, and they have a conserved baseline because Vanilla Ice actually sampled from Under Pressure when he made the song. So you can find this actually happens in many different domains. Copyright infringement, is one, just one example. So in summary, I'm just talking about specific applications here, but in summary, you have all these different things you can do with this. And it's not just limited to that. We're very much a data agnostic tool. And so what's happening is we don't make any assumptions about the data, right? We just compute on the data and give you what we think is a preserved pattern. You can then take insights from your particular domain and apply them to this to create things, to create new techniques and algorithms. And actually, when you actually do that, you gain the properties that we're giving you with the matrix profile, which is ability to accelerate it on the GPU, ability to compute it very quickly. There's a bunch of, you can get an approximate solution very quickly. And so there's a lot of different things that you can do with this. Yeah. Now I'm going to go into a little bit more detail about kind of what it means, what the matrix profile is, and how you, in terms of the algorithmic side, and how to compute it. So first, let's talk about what we call a distance profile. A distance profile is essentially you take a query for a subsequence in the time series, and you scan it across the time series. So as you do this scan, you can generate the distance. You can generate distances between every single point in the for every subsequence match. So you're basically taking one subsequence from the data, and you're scanning it along and checking for each time what its distance is. And so that gives you, for one subsequence, that gives you a one matrix profile value, which is the nearest neighbor for this subsequence, if you take the minimum distance, for example. So you generate a vector of distances, and you can take the minimum, And that'll give you the nearest neighbor, right? And the index. You can do this in O of n m complexity, where m is the subsequence length and n is the length of the time series, using a very naive method where you compute the dot product between every sequence. You can also do this in n log n complexity by using FFTs. I have a method cited here, which I'm not going to go into detail about because it gets a little hairy, but you're free to go and look at that later. But essentially, we use this method, which is essentially you convert the signal to the frequency domain. You can do this whole thing as an element-wise multiplication between the frequency domain values. And so this gives you the dot products in n log n time, which then can give you the distances in constant time after that, because you can compute the distances given just the dot products and the sequences and some summary pre-computed values of the sequence. So the matrix profile is essentially doing this. The simplest way to think about it is that you can do this every single time. So you can do this for every subsequence. You can run this algorithm and compute the dot products and then the distances for each row separately, right? And so this is parallelizable, but it's very slow. This is not actually the way you want to do it. This is an example. So it's essentially just a loop. Our algorithm is very simple. It's just a loop, and the loop calls this more complicated function, which essentially just computes these distances. Okay? So the time complexity of stamp is n squared log n, because you have to do this each time. For each consecutive subsequence, you have to perform this n log n computation. So this is still slow, but the space complexity is only O of n, because you only need to store the best so far, right? You don't need to store the whole matrix. So how do we scale this? So over the last couple of years, we have integrated some high-performance computing insights into the matrix profile. This has kind of been some of the core areas of my work, along with some of the algorithmic side. But essentially, we've learned a lot of things from this. Optimization is an iterative process with many moving parts. So if you have if you optimize one part of the problem and you don't fully understand exactly what's going on in the algorithm, you actually might be creating another bottleneck somewhere else. And so you can end up slowing yourself down unexpectedly if you're not fully aware of how things are moving around. And same thing for fast code. You have to be aware of the whole computing stack, from the operating system to the compiler to the hardware, right? If you want to make your code super fast, you end up writing assembly, which is not scalable, not readable. So thinking about the trade-offs between how you make your code fast, but also not completely incomprehensible to the next person that looks at it, is actually a very difficult problem, and it's sometimes not possible to get the best of both worlds. It's kind of like a choose 2 out of 3 kind of thing, in my experience. So we went from computing initially, this is actually work cited from our research paper. We went from computing in 4.2 days on one CPU thread and 3.2 hours on a K80 GPU for 2 million data points, to 6.5 minutes on 4 CPU threads and 5 seconds on a V100. So if you think about this, these are published results. This is a published result in a research paper. And you think about, like, if somebody just took our algorithm and implemented it, if somebody just took this and implemented it and said, oh, we're going to use this in production, and then they didn't optimize it, I didn't even calculate the speed up here. But if you think about it, this is, when you consider that we used a 40 GPU cluster to start running these bigger experiments, if we had used an unoptimized implementation to do this, we would have wasted thousands of dollars. So you might not even, the point I'm trying to make here is that you might not even realize you have a computational bottleneck, and you might not realize that you have a really easy like one-line optimization that you can do to actually fix this whole problem. It might be harder than that, but it might be actually that easy. It might be just that you're iterating your loops in the wrong order, right? That can cause problems with locality, right? So I just want to point that out. So we ended up using 40 GPU cluster to compute a billion length matrix profile. So this is an n squared computation where it's actually an optimized version of what I just discussed. So it's actually n squared. And so that leads to approximately 10 to the 18th pairwise comparisons. So this is, if you wanted to store this distance matrix, you don't try, right? This is 8, if you have double precision values, this is 8 exabytes. So you probably don't want to do that. And so in the end, this got cut off, but it's about 80 cents per quintillion comparisons, or per quadrillion comparisons. So if you want to do a smaller scale problem, you can actually do a pretty, like this, you can do a pretty good job of just not, just optimizing your code. You pay $1 to get a, to do, this is about 100 million or a 200 million length time series, or about 100 million probably. Yeah. So how do we get this speed up, right? Well, it's a number of factors. Better algorithmic complexity. We use tiling, algebraic improvements, architecture-aware code, and I'll go into each one of these specifically in a bit. And we use modern hardware, and relevant hardware features is really important. So things like the size of the cache and the size of the video RAM on the device, for example. So yeah, so this is just a disclaimer. This is a very high-level summary of some of the things we did to scale our application for specific insights into exactly what we did. We have our source code is open, and we have documented several papers that talk about kind of the experience we've had. So, and yeah. So first thing is algorithmic complexity. You don't actually have to compute every dot product. You can compute the first set of dot products, and then you can subtract off along the diagonals of this matrix. You can actually subtract off the first piece of the dot product and add on the next piece of the dot product, and you can generate this turns into a dynamic programming problem where you have a constraint along the diagonals of this matrix. And actually, this problem has existed. This formulation has kind of existed in mathematics for a long time, which we didn't actually realize until after we did it. In Hankel and Topless matrices. So if you're familiar with that, that's kind of might clue you in. So we have this computation along the diagonals now instead of row by row, right? And you can actually have, in the GPU, you can have a separate thread do each diagonal, and you can that improves your locality and your caching, because you're only accessing, you have these pre-computed arrays, and you're only accessing pieces of them that are local during your computation along the diagonal. And on the CPU, you can use a similar strategy. It's just not quite the same. So algebraic improvements. We went from this old update formula, which is just essentially taking the dot product and subtracting the initial values of the time series that computed that dot product and adding the next values. So it's sliding along the time series. But this actually has a lot of cancellation error, and so what you end up with is you end up having problems where you essentially have you end up having cancellation errors and all kinds of issues with stability in the algorithm. So when you try to scale this up to really large sizes, you end up getting the wrong answer because because of that. It's also, so when we converted to this factored formula, which has some mathematics in the background, which I'm not showing you, but essentially some of these values are mean-centered, and so you actually have a more stable algorithm. Smaller values being multiplied together results in less error, right? Yeah. And so this actually enables some single precision to be used in this computation for some data sets. For the distance calculation, this is the z-normalized Euclidean distance formula we were using, and this is the new formula which we're using for correlation. So we actually, instead of taking the minimum distance, we take the maximum correlation, and you get the same, you can actually convert between these two in constant time. But this can be pre-computed, this can be pre-computed. So essentially all you're doing is for this formula, you're going from this whole mess to 3 multiplies, right? Or 2 multiplies, sorry. So this is not only more efficient computationally, but it's also more efficient in terms of accuracy. So, okay, so another example is architecture awareness, right? So the initial GPU implementation didn't even do this, but in our subsequent GPU implementation, we had each thread doing one diagonal, but you can actually, we weren't saturating the bandwidth of the threads. So you can actually, load more values from memory per thread and get better performance because you have more locality. You can actually issue vectorized loads and from memory, and you can do all kinds of cool optimizations here, which results in less overhead on this very high performance GPU, right? CPU examples will be similar to this. So you can take the whole thing, and instead of doing, this is just one part of it, right? You can treat this thing as our initial problem. Now we can tile the whole thing into these triangular tiles. And then we can take a big time series and do the same thing across multiple, like a MapReduce architecture, right? So you can actually take this big time series, shard it up into these little segments, and then compute each one of these as a separate tiling scheme. So you have a multi-level tiling scheme coming down to just the hardware. And when you do this, you get these, you can get this huge performance benefit because you have all the locality and you don't really pay anything for it other than, you don't really pay a communication overhead because of this specific problem. In other problems, you might pay a communication overhead to do some of this, right? So here's some results. Oh, you got cut off. So we ran this on about 2 years at 20 hertz of earthquake data, and we found a bunch of really interesting things. This scheme enables fault tolerance, so you can actually lose a tile and be okay, right? Instead of, so you can run on spot instances, yeah. And so this actually gives you performance. This actually gives you a money savings, right? Because you can, because you're paying for the GPUs that are at the bottom of the bucket, right? And so nobody else bid for them, so you can take them for a third or a quarter of the price that they would normally cost to be non-preemptible, right? And so this whole thing took about 10 hours. And you can see that sometimes if you're using spot instances, you have to wait for compute time. But the GPU time was the same, and the spot cost changes because of demand, right? So what's next? So a bunch of these calculations are actually redundant, right? So if you think of back in the original, let's just find the time series. So a lot of this signal, this is actually earthquake data, but a lot of this signal is actually like seismic noise, A lot of this signal is the same earthquake. A lot of this signal is has similar behavior to other sequences in the time series. So maybe that we can compress the representation and actually do this in a much faster, approximate way, right? And so we can do this, right? We can take a time series subsequence, make a compressed data representation, and just predict a matrix profile value, right? And in doing this, we can have constant time updates and operate in real time, which means that we can deploy ourselves on potentially embedded devices if our network is small, if we're like, say we train on a neural network and you know, we deploy using TensorFlow Lite or some other, you know, MorphNet or, you know, something to optimize our computational efficiency on lower power devices, right? So you can take this, put it on lower power devices, and make decisions based on what's happening locally in real time, right? And so you can, that could be as simple as potentially sending data back to the server only when it matches some predefined template that you've decided on, right? And so that's one example of you know, something that's low-hanging fruit that we're pursuing right now. And then also, what else this computational pattern is not just for nearest neighbor. You can actually use it to do frequency, sum, histograms, other kinds of summarization methods on the data. There's some restrictions into like how much space and how many memory writes you're doing, but it actually is pretty flexible if you're within its domain. So, and that's basically it. The matrix profile, I just want to reiterate that this is a versatile tool, right? We are taking we're not making any assumptions about the data, right? So it's applicable to many different domains, and you can then provide your own insights into what you want to, what you're doing in your specific domain, right? And it can be computed very efficiently, as I've talked about. So yeah, it's already being used in industry. Target released a blog post about using it. There's several other companies, which I don't know if I'm allowed to talk about, but there's other companies using it. And there's also many implementations made by the community. So I have a CUDA and C++ version. There's versions in Python, Go, MATLAB. I think there might be even one in Ruby, but I don't know. Someone was asking about it, at least. So yeah, I'd like to thank all the people that I've collaborated with over the time that I've worked on this. And I'm here. This is me. So yeah, thanks, and I can take questions now.
Thank you very much, Zach, for that talk. Just a question. Is there a methodology to select the query size or the optimal query size when you are doing or when you are comparing a time series against itself? When you are
yes. So I've been asked this a lot. So the queries, so our only parameter is the subsequence length, right? But it's actually, we're not that sensitive to it, because when you have if you imagine that this, let me just go back to the first slide. So you can see that this pattern is actually longer than our subsequence length, right? So this total behavior pattern, right? It's longer than our subsequence length, but we actually have this curve that kind of progressively goes smaller until it hits a minimum, which is actually in several places, because this window, you have a window of this guy sliding over, and so he'll match in a couple places before it doesn't work. So what happens is that as you increase this subsequence length, this peak will get sharper and sharper, and it will actually progressively get smaller and smaller until there's no peak anymore, because it's just too small of a portion of a larger piece, right? And so what you can do is instead of computing with a large subsequence length first, you might want to look at smaller patterns. So you might want to look at local smaller patterns of length, say 100, or even 150, 200, 300. It changes the number of matches you find, but in the end, you'll still find the same longer matches. It just will be, it'll just be a longer, this will be like, it'll stay low for a while, right? So if you have a subsequence length of 100 and you have a pattern of length 1,000, there should be a valley of like length 901 or something like that, if the math works out. There should be a valley that for a long period of time where it matches. So I don't know if I answered your question, but yeah. You should just pick smaller subsequence lengths and it should work.
Okay, thank you, Zach.
Just not too small, because if it's too small, then you can get trivial matches, right? You can get matches which are false, right? Just because of the size of your data, and statistically, you're bound to run into a match.
Thank you very much, Zach, for the answer. So now we have a break, and it is time to have lunch. So the next talk will start at 20 to 3. Thank you very much.